we go over the dosing quiz, again, to get you ready for the final. All right, TR is a 32-year-old, 80 kilogram, I have to find my 5'10" male renal transplant patient who is 4 months post-surgery. He's been on 4 milligrams every 12 hours of Prograf. His CSS average concentration is measured in the lab as 40. Assume he's at steady state and the clearance and bioavailability remain constant. The team would prefer his concentration closer to 12. These are nanograms per ml, which is the same thing as micrograms per liter, right? Well, gotta find my stylus here. So he's overdosed. So we're concerned about toxicity, aren't we? So we need to recommend a new dosing regimen, giving so many milligrams every 12 hours, available as half 1 and 5 milligram scored tablets. The expected CSS average when on this regimen is how many nanograms per ml, round to the nearest whole nanogram per ml. And in order to avoid, okay, so we're going to first figure out a new dosing regimen. If he is at steady state and we assume that clearance and bioavailability are remaining constant, then we can use our proportion, can't we, because CSS average and dose rate are going to be proportional. So when he was getting 4 milligrams every 12 hours, so that's 8 milligrams per day, our patient had a concentration of 40 nanograms per ml, or micrograms per liter, and we're going to set that equal to how many milligrams per day to get 12 nanograms per ml. So we just do our simple proportion. So I'm gonna get my calculator, sorry. So 12 times 8 divided by 40 is, do that right, 4 milligrams every 12, 40, and we want to be at 12. So 12 times 8 divided by 40. So I got, this will be 2.4 milligrams per day. And we're going to give it every 12 hours. So we split that in half. So it'll be 1.2 milligrams Q12, but they come as 1 milligram tablet. So you could say 1 milligram every 12 hours, but as one of our astute students pointed out, is if you could split the 0.5, we could give 1.25 milligrams every 12 hours, which would be closer, wouldn't it, to our target. So either of those are acceptable, 1 or 1.25 milligrams of Prograf every 12 hours. And on that regimen, what would we expect to see as far as our concentration at steady state? Again, we can use this proportion, but instead of giving it trying to figure out our new dose rate, we're going to put in the dose rate. So if we're giving 2 milligrams per day, just make sure these units are the same, right? And then these units will be the same, nanogram per ml. So let's see, 80 divided by 8, I don't need to get my calculator out. It's going to be 10 nanograms per ml. If we give 1.25 or 2.5 milligrams per day, then it's going to be, I think 12.5, but so 2.5 times 40 divided by 8, is 12.5 nanograms per ml. So we would round that up to 13. So it's either 10 or 13 nanograms per ml for what we would expect for our CSS average. All right, so we've got too much. So how long are we going to hold the drug before we start our new regimen of 1.25 milligrams Q12? Well, this is a decay problem, right? So we are now at 40 nanograms per ml, and we want to get to 12 nanograms per ml. So here's our concentration, time decay, and we're decaying at K, aren't we? And we want to know what's this time difference. We want to know how long to wait until it falls to 12. So have we been given, so we have the half-life is 12 hours here. So we're going to assume that K is 0.693 over 12. So how do we set this up? We just have to do a little bit of algebra, which is so much fun. So remember, this is our peanut butter equation. So our concentration, our second concentration is going to be equal to our first concentration times e to the negative kt. T is what we're solving for this time. So our second concentration is 12 nanograms per ml. Our first concentration is 40 milligrams, or nanograms, I'm sorry, per ml. And then we have e to the negative k, which in this case is 0.693 over 12 times t. That's in hours, right? So now we have to do our algebra. So we're going to say 12 divided by 40. 12 divided by 40 is 0.3. Did I do that right? 12 divided by 40. Yeah, 0.3 is equal to e to the negative 0.693 over 12 hours t. Now we have to take the natural log of both sides, don't we? So what's the natural log of 0.3? It's negative 1.2, and then this becomes equal to, I'm sorry, no e then, negative 0.693 over 12 times t. So we want to isolate the t. These are both become positive. So 1.2 times 12 divided by 0.693 is 20.84. Is that what I got? I got 24 here. All right, so what did I get again? Let's see. 1.2 times 12 equals divided by 0.693. So 20.77 or 20.78 hours. So we're going to round it to the nearest practical. So that's going to be 24 hours, isn't it? All right. Moving on. Oh, I had that nice space. Oh, well. JP is a 15-year-old, 60 kilogram, 5'2" female renal transplant patient who is 4 months post-surgery. She's been on 1 milligram every 12 hours of Prograf. Her CSS average concentration is measured in the lab as being 6. So she's at 6 nanograms when she's given 1 milligram every 12. Assume she's at steady state and her clearance and bioavailability remain constant. Therefore, we can use our proportion. We want to be closer to 15. So this patient is underdosed, right? So we're giving 2 milligrams a day and getting 6 nanograms per ml. So how many milligrams per day? Oh my gosh, milligrams per day do we need to get 15 nanograms per ml? It's going to be a little over twice, right? So 15 divided by, or I'm sorry, 30 divided by 6. I don't need my calculator. we're going to want to give 5 milligrams per day, right? This is going to work out to be 5. So if we're going to give it every 12 hours, we're going to give 2.5 milligrams per day. And we didn't have to round or anything, so we're going to expect to get a concentration of 15 nanograms per ml. We don't have to put it back in because we know that when we give 5 milligrams per day, we're going to get 15. So if we need a mini loading dose, what would you recommend if bioavailability is 0.2, volume is 2? Okay, so to get a loading dose, remember to get a loading dose, it's just your volume times your concentration. And in this case, if we're giving it orally, we're going to have to give it, we're going to have to consider the bioavailability. Now, the other thing we have to consider is the patient already has 6 nanograms in their system. So the target is 15 nanograms per ml. But we're going to subtract what they already have in their system, which is 6 nanograms per ml. So we're going to want to increase by 9 nanograms per ml, right? And our volume is 2 liters per kilogram. He's 60 kilograms. So our volume is 120 liters, isn't it? And our bioavailability here is 0.2. So we're going to put our 0.2 in there. Can you read my mess? So our dose is going to be 9. So our liters, this is in milliliters. So this is in nanogram per milliliters, which is the same thing as micrograms per liter, right? So we want these liters to cancel. So 9 times, and our answer is going to be in micrograms. So 9 times 120 divided by 0.2 is 5,400 micrograms, or 5.4 milligrams, isn't it? So nearest 1 milligram, we're going to give 5 milligram for an oral loading dose there to make up that difference between 6 to 15. Okay? Our patient is diagnosed with epilepsy, wants to give a loading dose of valproic acid orally. The target CSS average is 75 micrograms per ml, which is the same thing as milligrams per liter, isn't it? Tablets come as 250 milligrams, round to the nearest 250 milligram increment. So the loading dose, we don't need clearance. We just need volume and distribution. So remember, our loading dose is being given orally, so we have to consider bioavailability in a salt form if there was one. So it's going to be our target concentration, which is 75 milligrams per liter. I'm going to put it in liters because our volume's in liters, times our volume, which is 0.15 liter per kilogram, times our 80 kilogram patient. So the kilograms will cancel, and we will have the liters will cancel, and we'll have our dose in milligrams, which makes sense, doesn't it? And now we need to correct for bioavailability, which is 90% or 0.9. So we just plug and chug. 75 times 0.15 times 80 divided by 0.9. And I got a 1,000. So we don't need, it's in milligrams. So our loading dose is 1,000 milligrams. So we don't need to make any adjustment there. All right. Question 4. So here we have a patient that's admitted for atrial fibrillation with a rapid ventricular response. We're going to start them on PO digoxin, with a goal of 1.2 micrograms per liter. The patient has normal renal function. Okay. So what would be an appropriate oral maintenance dose for this patient? So we're now going to start with our CSS average equation, right? So our target here is 1.2 micrograms per liter. And it's going to be equal to our bioavailability, which is 0.7, times our dose rate, which is our unknown, divided by our clearance, which is 0.107 liters per kilogram per hour. And our patient weighs 82.3 kilograms. So the kilograms will cancel and we have liters per hour here. The liters will cancel and we'll end up with a dose rate that is in micrograms per hour. Micrograms per hour, right. So let's plug and chug this one. So 82.3 times 0.107 times 1.2 divided by 0.7. So our dose rate is 15.1 micrograms per hour. And we're going to give this every 24 hours. So we're going to need to multiply that 15 micrograms times 24, aren't we? Times 24. So we're going to have a dose rate of 362 micrograms Q day, right? Every 24 hours. But we want to have that in 125 milligram increments. So I'm going to divide that by 125. We can see it's about 3. So 3 times 125 is 375 micrograms per day. Okay, that's not too bad, is it? We're going to do one more and then I'm going to need to take a break. Okay, this is the same patient, but now we're going to give an IV loading dose for this patient. So that's simple because it's IV, so we don't have to worry about bioavailability. We also don't have to worry that the patient's on anything already. So our target is 1.2 micrograms per liter. And now we just need to multiply it times the volume to get our loading dose, right? So our loading, let's see, our volume is 6.5 liters per kilogram, and our patient weighs 82.3 kilograms. So the kilograms will cancel. We have liters and liters will cancel, and we have micrograms, which is an appropriate loading dose. So that makes sense. 1.2 times 6.5 times 82.3 is, let's see, I got 641.94 micrograms for our loading dose. And again, we want to round it to the nearest 125, so I'm going to divide it. So it's basically, that's like 5 doses. So 5 times 125 is 625. So we're going to recommend an IV loading dose of 625 micrograms. All right, that's the first 5 questions, and I'll come back in a second video with the last 5 questions. Thanks for your patience.